Hey guys, this is Mrs. Harbin, and we are going to continue in our unit on radicals and roots. We have spent some time changing from radical form to exponent form and exponents back into radicals. We have really tried to get a good understanding of why we call it a squared root and a cubed root. We've looked at our perfect squares and our perfect cubes. We've estimated using a number line where different roots might be based on our perfect roots. And so now we're going to look at some roots that are not perfect and figure out how it is that we can simplify these when they're not perfect roots. Our biblical application for this unit is that God blesses his people with the abilities and skills to succeed in their life work to his glory. Each of you has different gifts and different talents. For some of you, this is going to come easy, and for others of you, it's going to take a little bit of work. But he has given us different gifts and abilities, not so that we can waste them, not so that we can just hide them away and, use them when we feel like it, but to succeed in the task that he's called us to do, to pursue a job, to pursue a career, to pursue our passions and our interests with the intention of bringing him glory. And that's definitely what we want to do with the math that we are learning. We're not just learning it just to learn it, but we're using our ability to think and the logic and to reason to be successful in future careers, future jobs, and taking care of creation, and all of that is for his glory. The lesson objective for today is that you, the student, will use rules and properties to simplify radicals. Now, last week we talked about prime factorization, and we went over how to do the prime factorization of numbers, just as a quick review. And so see if you can go ahead and on your own, on your notes, do the prime factorization of these numbers. Pause it, do the prime factorization, resume the video to check your work. So there's a couple of different ways that you can do prime factorization. We looked last week at doing it using a factor tree. Taking 4 times 8 and dividing it into 2 factors, maybe 4 and 12, and then recognizing that these are not prime numbers, so we factor it again. Okay, 2 and 2, those are prime numbers, so we're done. 12 is 2 times 6, and 6 is not a prime number, so we keep on going until we end up with all prime numbers here. And then we would write that as 2 times 2 times 2 times 2, so 2 to the 4th power. Times 3 is our prime factorization. We also looked at a different way to do that, and Jonathan called that the wedding cake method, taking the number and dividing only by prime numbers. So 2 goes into 48 24 times, and 24 divided by 2 is 12, and 12 divided by 2 is 6, and 6 divided by 2 is 3. And so then it looks like we've got this kind of layered cake, this wedding cake. But when we look at the prime factorization, you'll see that it's exactly the same. 2 to the 4th times 3. So check your work and make sure that you got each of these prime factorizations correct. Okay, we won't go over those. This was just kind of a warm-up. Go ahead and try these as well. Pause the video. Try to factor these according to our prime factorization method. Come back and check your work. You should have gotten 2 cubed times 3 times 5 squared, and 5 cubed times 7. It's really important that we can do prime factorization before we go into simplifying radicals. So if you are struggling with this, make sure that you get some help from me before we continue. When simplifying radicals, we know the reason why is because in mathematics, answers are generally expected to be stated in the simplest form. If possible, we want to get rid of parentheses. We want to get rid of grouping symbols. We don't want any exponents. And in the case of radicals, we want to use prime factorization to simplify our radicals so that they're in simplest form. When a radical is in simplest form, its radicand contains no perfect power factors. So we're going to look at the factors of the radicand and see if any of those are perfect factors. Even though the whole number might not be a perfect square or perfect cube, it might have factors that are perfect squares or perfect cubes. Let's take a look at what this looks like in the product property of radicals. The product property of radicals says that for x being greater than or equal to 0 and y being greater than or equal to 0, if we've got these two factors underneath a root symbol, we can actually split them apart. So if I have 2 or more things being multiplied that are not equal to 0 under a root symbol, I can kind of reverse distribute those factors and apply my index to each of these factors individually. So let's take a look at the square root of 24. Now 24 is not a perfect square, but if I factor 24, I might find out that some of its factors are perfect squares. So let's go ahead and list the prime factorization of 24 as 2 times 2 times 2 times 3. Now this is a square root. I have an index of 2. So I'm going to be looking for factors that show up twice. And I see that 2 times 2 forms a group of 2. Now there's another one, but because I'm doing an index of 2, I only want groups of 2. I don't want groups of 3. So I'm going to split this apart here and put each of my groups of 2 in their own separate root symbol. So when I write that, I'm going to write the square root of 2 squared, and then the square root of everything that's left over, which in this case is 2 times 3, which is 6. Root symbols and exponents undo each other. They are inverse operations. So the square root of 2 squared, it undoes each other, the square root of 2 squared, and all I'm left with is 2. Now, if you want to see why that works, the square root of 2 squared is really just the square root of 4, and the square root of 4 is 2. So you can multiply that if you want and then take the square root, or you can just know and learn that the index cancels the exponent of the same thing. Let's write that in exponent form. We know that this would be written as 2 squared over the index of 2, which is 2 to the first power, which is just 2. So there's a couple of different ways that you can see that the index undoes the exponent here. So the square root of 2 squared is just 2, and that's being multiplied times the square root of 6, which cannot be simplified. It doesn't have any factors that are perfect squares. And so our final simplified answer is 2 square root of 6, or 2 root 6. Remember that the implied operation here, what's happening between the 2 and the square root of 6, is multiplication. Let's go ahead and simplify 75, the square root of 75. I know it's not a perfect square, so let's use prime factorization to see if any of its factors are perfect squares. The prime factorization of 75 is 3 times 5 times 5. Again, I have an index of 2, so I'm looking for factors that I can group into groups of 2. And I see a 5 times 5, a group of 2. So I'm going to rewrite that as 2 times the square root of 5 squared, and then my leftover part, square root of 3. I don't know why I said 2 times. Square root of 5 squared and square root of 3. Now, based on what we know before, if I were to write 5 squared, square root of 5 squared as an exponent, I would have 5 to the second power over 2, which is just 5 to the first power, which is 1. Or I can just remember that an index of 2 cancels an exponent of 2 under the symbol. So that's going to leave me with 5 times the square root of 3, or 5 root 3. Let's try the cubed root of 40. The first thing I need to do is the prime factorization of 40. And when I do that, I get 2 times 2 times 2 times 5. This time my index is 3, so I'm looking for factors that are repeated 3 times. And I see that 2 times 2 times 2 is repeated 3 times. That's 2 cubed. So I'm going to rewrite my radical here as a radical of 2 cubed and a radical of my leftover parts, which in this case is just 5. Now, just like before, 2 cubed with an index of 3, if we were to write that as a base and exponent, would look like this. And 3 over 3 is 1. So it's 2 to the first power, which is just 2. Or we can remember that the index cancels the exponent if they are the same. So the cubed index and the cubed exponent, they cancel each other out. So we're going to be left with 2 times the cubed root of 5. 5 does not have any factors that are perfect cubes. So 2 cubed root of 5. When simplifying radicals, follow these steps. First, Write the radicand as the product of its prime factors. So do the prime factorization and list each of the factors. Then apply the product property to the perfect powers. So if we're taking the square root of something, we're looking for groups of 2, since the square root is an index of 2. So like 2 times 2. If we're taking the cubed root, we're looking for a factor that's repeated 3 times. If we're taking the fourth root, we're looking for any factors that are repeated 4 times, etc., etc. Then we're going to split apart that radicand into separate radicals using the product property. Then we'll simplify the roots of the perfect powers. So a square root cancels a squared exponent, a cubed root cancels a cubed exponent, etc. And we'll multiply the factors inside and outside the radical. Let's take a look at this example, the square root of 648. So the first thing we're going to do is prime factorization. When we factor that out completely, we get 2 times 2 times 2 times 3 times 3 times 3 times 3. This is an index of 2. It's not written, so we know it's implied. So we're looking for factors that form groups of 2. So here's a group of 2. Here's another 2, but it doesn't have a partner to make it a group, so we're going to leave it alone. Then we've got a group of 2 here and a group of 2 here. Then we're going to apply the property that allows us to split apart our exponents here. And we're going to get square root of 2 squared, square root of 3 squared, square root of 3 squared, and then our little leftover 2, square root of 2, goes down here at the end. Knowing what we know about exponents and roots, we know that a squared root cancels a squared exponent, so these will cancel, and these will cancel, and these will cancel. So we're left with 2 times 3 times 3 times the square root of 2. Our last step is multiply anything on the outside to simplify. So 2 times 3 times 3 is 18 times the square root of 2. We cannot simplify this anymore because it doesn't have any factors that are perfect squares. All right, see if you can do this one on your own. Pause the video and come back and check your work when you've had a chance to try it. Okay, when factoring 14,580, we get 2 times 2 times 3 times 3 times 3 times 3 times 3 times 3 times 5. We're going to list all those out individually, and because we're taking the cubed root, we're looking for groups of 3. Now, my 2's, there's only 2 of them. They don't form a group of 3, so I'm going to leave them alone. However, I have a group of 3 here, and I have a group of 3 here. I don't have any groups of 3 of my 5, so we're going to leave that alone. And we're going to split apart our radical and rewrite this as cubed root of 3 cubed, cubed root of 3 cubed, and then the cubed root of our leftovers, which in this case is 2 times 2 times 5. We know the cubed root and the cubed exponent cancel each other out, so we're left with 3 times 3 times the cubed root of 2 times 2 times 5, which is 20. We multiplied what was inside or under the radical symbol and put that here. Now we need to multiply what's outside the radical symbol, so we end up with 9 times the cubed root of 20, or 9 cubed root of 20. All right, try this one. The steps are the same. Don't let the letters throw you. Let's go ahead and do prime factorization. And the prime factorization is actually skipped right here, but the prime factorization of 32 is 2. Let's write it up here. 2 times 16. 16 is 4 times 4. And 4 times 4 is 2 times 2 times 2 times 2. So 2 times 2 times 2 times 2 times 2, 5 2's, times x times x times x times y times y. Okay, I've got 3 x's and 2 y's. Because I'm taking the square root, I'm looking for groups of 2. 2 times 2, 2 times 2, there's a leftover 2. 2 times x, there's a leftover x, and 2 times y. Okay, so I would write that as square root of 2 squared times square root of 2 squared times square root of x squared times square root of y squared times my leftovers, which is I've got a 2 and an x left over. Now, you can see on the notes here, they skipped right ahead to 16. Instead of writing the prime factorization, they recognized that 16 was a perfect square. So they just separated the 16 and the 2. I would like you to do it